All right. How about you?
Is that it? You ready?
Yep.
Okay. Well, thanks, Jordan, and thanks to everybody at UMass Amherst for hosting this. I'm going to go ahead and just jump right into the slides. I will share the slideshow here. You'll only be able to see that, but you'll be able to hear me. And then at the end, I will jump back into this to take questions, if that works for everybody. And if there's anybody that has a question in the meantime, feel free to speak, and I can answer that. But I think probably best thing is just to kind of save them to the end. So without further ado, I'll go ahead and share my whole screen here and get started. So I am Andrew Kemendo, CEO of Pear Inc. And if you want to get me on Twitter, I'm at Andrew Kemendo. Or if you have any specific questions or want to get really any more information about what we're talking about here today, you can hit me at Andrew at pear3d.com. So just brief overview here. Going to talk briefly just who I am, what do we do at Pear. If you don't know what AR is, I'm going to cover it very, very lightly. Just kind of broad overview because we're going to get into the depth later on, and then we'll start talking about the actual, what we consider a stack. And that's the next three pieces, which is environmental understanding, display, infrastructure, and content. And then we'll wrap up with questions. And I'm hopefully going to leave enough time that we have a lot of good questions, because there's a lot here, and there's a lot I also don't cover, for whatever that's worth. So who am I? Long time kind of technologist, developer, you'd call it. Back in the 90s, when I was 7 or 8, I built my first side-scrolling game, wireframe and all that. It was Dennis the Menace, based on Mario Brothers. Didn't go anywhere, but that's okay. Built my first robot in mid-90s. You can see that, the roaming robot. That was one of the kits that I got. Really exciting there. And then I started building 3D games in different engines. 3D Rad was one of the first ones I used. Decided to join the Air Force, go fly planes. At least I thought I wanted to fly planes. And started 2003, ended up graduating the Air Force Academy 2008. Went on to be a intelligence officer, served in the Middle East, Pacific, and then here in Washington, D.C. area. When I was out in Guam, actually, I had a need for a architectural visualization tool that didn't exist, and I wanted it to be an AR tool, an augmented reality tool. So I started building kind of a crude prototype, worked with some folks over in Germany to help with the AR aspect of it. And then that went well enough that when we moved here to Washington, D.C., I was able to find my co-founder, Taylor Clark, and he was able to kind of rebuild from scratch and kind of took it from there. In the meantime, I was pursuing a master's in artificial intelligence here at the National Intelligence University, and then left the military in 2015 to go full-time with what at the time was called VisDraft. That was an architectural visualization tool. And then in August of 2015, we had so much demand for a product-based AR tool that we kind of re-engineered everything to release and kind of rebrand as Pear. So Pear, you can see here briefly, it's really the best way to see products in your space in real time. So you can, as you can see here, the user is dragging and dropping the product into their space, and then he can do, he can do multiple objects. It's not restricted to just furniture, by the way. This is just kind of our starting point. As you can see from the video, he's walking around. That's real-time actual movement, so he can, no kidding, see 360-degree view. It's 6 degrees of freedom is what it's called. Here you see just kind of the view from your iPad or your iPhone, what you'd be seeing. And this is all markerless. We'll talk a little bit about that. You can do an entire setup. You can jump out to the shop and go to go buy it from there. So it's really the best tool on the market, bar none, and by far for doing AR room planning. And really, that's going to expand in scope here soon. So augmented reality generally is the idea that you're overlaying some kind of virtual element onto the real world. This is a video from Microsoft's HoloLens demo. It's not perfect, and it's not exactly representative of what the HoloLens can give you, but it is a pretty good overview of what the applications of augmented reality are. So you saw a person in his home kind of just doing some casual applications. Here you see a woman in a design shop actually doing some engineering with it. In terms of realistically, these are good applications. How it's going to work in practice will be a little different, especially when you consider different things that we'll talk about, like field of view, the actual interface, the form factor. But as you see, all of these kind of gaming, all these instructional capabilities, these are what encompasses what we're talking about with capabilities for augmented reality. Here you see some mock-ups of doing things on Mars and doing it in a way that you couldn't get through a regular 2D interface. It's a great tool for design. Really where we are today is kind of starting that whole design process. We use elements from our manufacturers, but in the end, it's still a design process. So you see, really, it covers the entire computing gamut. And what we're really excited about is that in the next, call it 10 years, this is going to be the computing and really communications platform that everybody will be on. Now, it's part of why we like to give these talks is so that we can start getting people into how do you build these worlds. And so when we see here on the left, obviously there's what's real. In the middle is the AR aspect of it. It's that overlaying. This is distinct from virtual reality in that you're not going into a closed world. You're actually staying inside the real world, and you're putting new elements into it as though they were real, so that they're convincingly, I guess you could say, tricking yourself or tricking others into believing that this virtual object is real. And again, those applications that you saw kind of show you why that matters and why we want to do that. So we'll go ahead and jump into what we consider the stack. Now, for any software developer out there, you know what a stack is. It's kind of the component parts. I don't follow that perfectly, and then I'm not going to give you every single tool or piece of language that you need to do this entire thing, but it will give you the basic 3 layers, or what we consider the 3 layers that you need for what is considered hard AR. And hard AR is where you have what's basically shown in the HoloLens video, where you're wearing something on your face and you have a actual, no kidding, real convincing view to it. And there's a couple little caveats in here that we'll work through, but the main thing that you need to understand here is this: AR broadly, augmented reality broadly, to do it right, it's really a system of systems. So the environmental understanding part of it is its own system: mapping, tracking, loop closure. The AR display system is its own system also, or sorry, the AR displays comprise their own system as well. So that is the internal tracking. That is how are they doing actual rendering, what kind of 3D environment is inside that, no kidding, display. So that's its own system. And then the content and applications, really what we consider infrastructure, is all of the layers that you need in order to enable all of those other pieces. And they all work together. Not one overtakes the other. But when you start to kind of get into how do you build this out, there's a couple ways you need to understand where your starting point is. So you can start with hardware, or you can start with your application. But once you do that, then you have to make your choices on all the rest. So for example, if you start with AR display as a hardware, then you need to figure out what are the options for environmental understanding, and on and on. So this is just a really crude overview of the kind of system that you need to just strictly understand the world around you to do augmented reality. But this gives you an example of one of those systems that is within the kind of broader AR environment, and we'll talk about that. So there's really 2 approaches right now to augmented reality. There's marker-based and markerless. So marker-based is what you see here. So she puts down an actual piece of paper. In this case, it's an IKEA catalog. This is from 2012, and she's walking around it using that as a actual reference point. So this has been around a long time, since 2007 from a commercial standpoint, and long before that from a engineering standpoint. And it does have some advantages. It's easy, it's cheap. You can recover scale very quickly because you know the size of whatever that is, that piece of paper or whatever you're looking at is. However, it is cumbersome, so you always have to have some kind of something in the real world. In this case, it's typically a printed out QR code. It's kind of advanced over the years so that now it's image based, and there's a lot of capabilities out there that are image based. So you're not using QR codes. You can use, for example, a movie poster. Also, you could consider that a 3D understanding, or in other words, looking at something, understanding what it is in 3D. So, for example, you have a flower vase. You could consider that a marker too if you do it in a certain way. Even still, those lack applicability because you're typically tied to that. In other words, once you have kind of locked onto that target of marker, you really can't deviate far from it in order to kind of maintain that AR capability. So it's not like an initialization tool. It's something that you kind of have to have in view all the time. And that's not 100% across the board, but for 99% of the cases, that is the case. So this is Markerless AR. This is in-app view from Pair. And as you see, we don't have any markers, and this was me dragging and dropping a couch into my living room at Christmas time. And now I can walk around it with 6 degrees of freedom. That means move around in the vertical, horizontal, basically all 360 degrees around whatever object or whatever environment I'm in without a marker. Okay, so that's when we talk about markerless, that's really what we're talking about. So again, advantages there, you have really full freedom of movement. You can continuously move around wherever you are, and you're tracking your space. Again, we'll get into that, but you're tracking your space, which gives you that flexibility. It's a lot friendlier user experience. So it's typically the user experience that you get with other types of 3D applications. Also, you don't actually have to print anything. You don't have to have any kind of outside reference. And it has wide applicability, so you can do lots more. You can do a lot more things with it than strictly just kind of put something on the floor, put something on the wall, and use that as a reference point. That said, it is very difficult to build. So we'll talk how you kind of build some of the stuff, and the rest of the talk is going to be focused on markerless. I'm not going to talk anymore about marker-based approaches because those are kind of done to death, and there's not really a whole lot more excitement in terms of how do you develop for that. Markerless is absolutely the future. It's what we're already doing, but it's dominant at this point. At the same time, it's complicated. It's difficult to build. It's also complicated to get some of the scale aspects, at least more complicated than having a reference frame. And there's a bit of overhead computationally that you don't have with a marker-based approach because of some of those other things. That image to the right is just an example of how you do tracking kind of within this kind of markerless frame. Okay, so let's just jump right into the kind of first piece of the stack, which is we consider environmental understanding. And as part of this environmental understanding, you have to do 3 things, and these three things are done simultaneously. You can initialize at mapping or tracking. In other words, you can already have a good map of your area, or you can start with no map and begin by tracking in order to build a map. But once you do initialize, you have to do all 3 of these things together in order for it all to work. So when we talk mapping, that's, no kidding, actually taking a virtual copy of whatever's around you. That's so that we can have a accurate scale representation. That's so we can have a accurate tracking mechanism so that you can kind of derive from the key points around you, where you are. Same thing with tracking. Tracking generally falls out of mapping to some degree with a couple of extra steps, and that gives you where the user frame is. So in other words, where is the viewpoint coming from within this world, within this world that you've started to map. Putting that all together is called loop closure. So that's its own subdiscipline, where you're taking the pieces from mapping and you're taking how you're tracking and actually kind of keeping those together so that you can have an accurate view frame of this, what we consider this metaverse. So this is how, for example, Pair does its mapping, and you can see here it shows you the actual viewing frame. This is a SLAM implementation, which it's simultaneous localization mapping. I'll get into that briefly, but as you see here, this is a point cloud representation that's being built from that map. Now this is monocular. That means there's a single camera, and you'll see, and we'll talk about stereo rigs and all the rest, but this gives you an example of how you can do some mapping given different viewpoints with a single camera. From this, it's a little bit of a step, and it's kind of outside of the box of mapping, but you can take those and you can do some surface reconstruction. You can do some meshing to rebuild that world. Now, obviously, this is not the same one from the previous video, but this shows you a view from my living room of a couch that we've got. And this is just straight off of the point cloud that we take in the map. But it gives you an idea of how we can start building that metaverse at the same time that we're tracking and keeping track of really where we are in that frame. So there's a couple ways to do this. External tracking is what you see with, for example, the HTC Vive in their Lighthouse system. This is very popular in VR systems, it's been popular basically forever because it's fairly easy to do. You have an IR basically light that's you can see there in figure 3. Or indicated there with number 3, and that IR light basically sends out that structured light, and then it reflects back all of these different retroreflective coated kind of balls, and each of those are mapped internally to the system, and then you can track those within a 3D reference frame, and that gives you your where you are in the world. This is almost irrespective of what the map is. So we're not going to really talk about this much because it's not really applicable to AR in a broad sense. But that doesn't mean that it's not possible or it's not a possible solution. So the idea here is just to introduce you to a lot of these concepts so that you can see kind of what's out there. In order for external tracking, which is also called outside-in tracking, to really work at scale, you'd have to have IR, basically illuminators around the world and kind of everywhere inside of everything, and that's just not practical. Instead, what the kind of way everything is going is, and it really has gone for the AR world, is internal tracking. We consider this inside out. So you see 3 kind of implementations of that in terms of hardware that you can use to start building that tracking system. RGB camera, which is what we use, it's a single monocular camera. It has some challenges in that you don't get all of the depth data immediately. We've been able to get really true monocular tracking from a single camera, and that's what monocular means, but we've been able to get tracking from a single camera only really recently, in the last 5 years or so, and especially on a commodity device like a phone or a webcam, and that's really what we're most excited about. But there are some drawbacks to that. One of the main drawbacks is that you have to have good lighting, you have to have a scene that's fairly easy to interpret, and when I say easy to interpret, that means it has features to it. So you're not looking at just a flat white wall, for example, or a single color image, because there's nothing to track. Kind of beyond that, you can start adding extra sensors. So IR emitter and IR sensor gives you a better depth estimate kind of immediately right off the bat. And that's what you see with the Kinect. That's what you see with the RealSense cameras, the Google Tango system. That uses this IR system in order to get that depth estimate so that you understand immediately how your world kind of works. So it helps with both mapping and tracking, but it's largely used to do the really kind of high precision tracking. Now at the very highest end, well, it's not really the highest end, because the highest end are AESA radars, which are active electronically scanned array radars, and that's what's used on, for example, like the F-15 and the F-35 and the F-22. And these are very complex radars. But kind of a step back from that is ultrasonic ranging systems, which you see on some mapping robots. Those actually do send out higher frequency ultrasonics in order to get a very high resolution understanding of the world around you. Less good for tracking because it doesn't necessarily give you back your positional estimates. You kind of have to do some of the same things you do with the RGB camera with the ultrasonic system. In those cases, it's something called FTDT, which, if you are familiar with any type of kind of radar imaging, you'll know FTDT. But that's kind of where we think that the very high precision sub-millimeter tracking and mapping is going to go, kind of to that ultrasonic side of it. So here's an example of an internal track system. This is Group 13th Lab. They were acquired by Oculus about 1.5 years ago. And from what we understand from what Oculus is doing is, as opposed to the external tracking of, like, for example, the HTC Lighthouse system, the Vive's Lighthouse system, they're doing everything internally, which, again, that goes back to the inside out, and that's where we see the real benefits of these systems being used for AR systems. Now, the question is, does that mean that Oculus is going to release an AR headset in the next 5 years? Well, maybe, but we don't know. And this is really the kind of the way things are done. Things are going to be done all in the future for tracking. I talked a little bit about loop closure and what that means. So what you'll start to see here is a mapping system that's also tracking. So you see there in the green, that's actually tracking where the person is in the view. What's being mapped is obviously the mesh return that's kind of encompassing everything. I won't go into the specific red lines and what they're doing, but you'll see what happens briefly here is when they rotate around, something will happen where the kind of end of their tracking loop, they re-reference, and you'll see it happen real quickly here, that the kind of left side of one part of it matches up to the right side of the kind of starting track. Now that's considered loop closure, and that's how you get a really comprehensive understanding of kind of high accuracy, what is in my world. This is done, I mean, you can do this with any number of those sensors that we talked about. The level of difficulty ranges depending on which particular sensor you're using, but this is an absolutely critical piece. And the reason we talk about this, and you'll see it happens again here with this outdoor walkthrough, is that if you don't have a loop closure system, when you walk into a known environment, you'll be off by some factor. In other words, my virtual, that metaverse I was talking about, that virtual representation of the world, if we don't have a loop closure system, it will not be stuck to the real world accurately. So when you do try to put new elements within it, anybody who wants to come and interact with those, they won't be able to see them because they'll be at the wrong place. You see this, for an outdoor scene on a larger scale that happens. Here's an example of how it's done vertically. So 2 different floors of a place being closed, having that loop closure system happen. And again, it all comes back to how do you marry up the real world and the virtual world. So this is an absolutely key component into building that metaverse that you need in order to place, no kidding, new objects in it for everybody to share. So we'll move on from there. Just to kind of wrap up the environmental understanding piece of it, from a technical perspective on the underpinnings, for all of you who are saying, okay, well, that's all great, how do I get into this? These are the kind of 4 areas that you need to understand. Is the SLAM, which is the simultaneous localization and mapping, and there are derivatives of SLAM. So there's parallel tracking and mapping, which is PTAM. There's dense tracking and mapping, which is that's DTAM. Visual odometry is what's behind the tracking system. The sensor fusion is how you kind of do a lot of this stuff with a monocular system. I'm not certainly going to go into the details of any of these because they're talks in and of themselves, but at least this gives you kind of an overview of the general principles. When we talk external reference, that goes back to the kind of external tracking piece of it. I don't necessarily think that would be a really great place to start. However, it is good to understand kind of how that works, because some of these systems can be integrated. So for example, GPS today is not accurate enough. It's about 3 meters off typically on a kind of a good day. However, CD GPS, which has been around for a while, has sub-centimeter accuracy, and there's been a big push kind of recently to try to integrate CD GPS systems kind of within the US. I don't know if that's going to take off. It's kind of a hardware question in terms of what people are going to put onto mobile devices, but it's a possibility. So it's worth kind of at least exploring a little bit. In terms of what kind of tools you're going to use, unfortunately over the last year, there were a slew of acquisitions that took a lot of these tools off the market. So SDKs, APIs, so for example, 13th Lab had one that you could utilize. Mateo was a big company that you could build applications with for AR specifically. Excuse me, now they're gone. And you pretty much have to build everything from scratch right now with either open source tools or kind of building your own. So from a computer vision standpoint, there's a couple libraries that are open source, libccv, OpenCV, the reconstruction, there's a structure from motion systems that you see there, or really you really would probably have to kind of roll your own. And that's at a fundamental level. You need to really have a very, very good understanding of your programming languages. You need to have a very good understanding of physics. You have to have fantastic understanding of mathematics and how to do all the transformations you need to do, because they're very cumbersome. I will say that in order to build one of these systems, it's not sufficient probably to have a PhD in computer vision. It's a good starting point, and it will get you deep enough to start off, but you need practical experience. You need to work with a robotics club. You need to buy some of these sensors. You need to start building some of these things. You're not going to be able to just pick it up overnight, because there's just too many variables in any of these cases that you're going to just run into. Okay, so next up is kind of the sexy part, and this is what's taken most of the press basically since, well, more or less forever. Very few people talk about the mobile infrastructure. Very few people talk about the kind of metaverse aspect of it, largely because they don't know, quite frankly. But what's tangible, what you can see and touch and feel, are the displays. So we really look at it from two aspects: the mobile device display and the head-mounted display. We at Pair focus on mobile displays strictly because, well, there aren't really any head-mounted AR displays worth the name today. Google Glass doesn't count because it doesn't do any tracking or mapping. It doesn't actually interact with the real world in any type of functional way from a vision perspective. There are a handful of other products out there, Epson Moverio, which I'll show you a brief video of, that do a better job, and that they have a 3D representation engine behind them, but they still don't do the kind of fundamental things you need to do, which are those tracking and mapping aspects. So we've focused on mobile because the applications are there. In other words, we can build an application around it that gives that true kind of augmented reality experience, the 6 degrees of freedom, the convincing nature of putting things into your real world. And do it in a way that billions of people have accessibility to. So, market penetration for smartphones is basically everybody who's connected to the internet in the world right now has one. It's absolutely massive, and it's not going to go away anytime soon. It's only kind of growing more, and more advanced devices are getting into more and more people's hands, which is great. More computation, better cameras, better systems, better access to internet, which is a big key component. You'll see, obviously, you have to have that. You see there below the Project Tango. That is a mobile device that has those depth sensors on it. There's a Lenovo phone. There's a Qualcomm phone the Qualcomm phone, I guess, is out. The Lenovo phone is going to be coming out in the next couple of months that has some of these. Question is how widely applicable are they going to be? It's a big question. We don't know. I don't think that it's probably going to be that applicable. I think that we can do enough without them that people won't demand them. But anyway, so focusing on commodity mobile is big. But head-mounted displays really are the future. So 10 years down the line, that's going to be the computing platform. So there's a couple things that we need to talk about kind of on the front end in terms of what matters in the heads-up display or head-mounted system. The first is field of view. And there's a lot of talk around, or there was a lot of talk early on with VR systems of what are the VR systems' field of view? Is it enough? Is it too little? What's too much? This kind of thing. And the Oculus and the Vive Both fall somewhere around 110, 120 degrees. Your average phone gives you about 60 degrees. Now you can do a couple funky things to get a little bit wider than that, um, and there's some add-ons that you can do to get wider, but that's about what you'd expect for the commodity device. Different again between devices as well. The HoloLens, which has had the most publicity to date of a truly AR system that does tracking and mapping, has about 40 degrees. So you would expect that that's about the field of view of having a laptop in front of you around about 3 feet away. So we think that this is insufficient, and we'll talk about a little bit, what we think is needed. But field of view is probably one of the most important aspects of it. Accommodation is the second one. If you're not familiar with accommodation, that means that you can focus at different focal lengths within your viewing plane. So just as you do now, if something's very close in front of you, you can focus on that. If something's very far away, you can focus on that as well, and everything in between in incremental steps. So having that ability brings that real world kind of that real world function to it. That accommodation is absolutely humongous. To date, we haven't seen any system that actually has an accommodation capability. There are ways to kind of fake it, but it's very cumbersome, and you end up kind of, I don't want to say straining your eyes, but it's not quite comfortable because it's almost like a manual process. Whereas with real life, you don't have to think about it; you just do it, and it's immediate and it's very fast. So as you see here, this image shows you kind of the difference in how you do that focal length change. And this is with a camera, so it's not exactly a perfect representation, but at least it gives you the idea of how you're changing focus at different depths. And the last, there's a ton of factors here, but the last factor that we think is going to be critical for kind of consumer adoption is this form factor. On the left, you see a product called 3D Head that got universally panned when it came out at, I think it was CES in 2015. That's the opposite of what you want. You look like a clown, and nobody wants to go there. In the middle, the form factor is exactly what you see. It's the phone, and it's what we have today. It's good enough that we're seeing fairly large scale adoption, and people are comfortable with it. That's kind of one of the big keys too, is that people need to be comfortable with it. In the end, though, what you see on the right there with a very sleek and kind of more traditional design for a heads-up display is really where we're going with kind of that's where it needs to be in the long term in order for people to be comfortable with that system. So from the head-mounted display approach, there's really two kind of technical ways to do it. There's microprojection and virtual retinal display. So here's an exploded view of the Epson Movario, and what I'll do is I'll pause this and kind of talk about it for a second. What you see here is this is one lens, and this is a waveguide system. So you see here all the way from the first lens through a series of other lenses, and then into a waveguide system to what you see here is basically a wedge, and at that wedge you have reflected what comes off of this micro LCD OLED screen that's very tiny, and this is basically it. So you have one on each side, and they're replicating what you're projecting from, or what you're basically feeding it from some other system. So it's whether it's a wearable computing system or a desktop-based system, that's where the image is feeding from, and you do a combination of stereoscopic effects in order to make the image look 3D. But as you see here, it's at the very basic level, it's an LCD. Now there are some things you can do. So you see, this is kind of their, actually this video came out today if I remember correctly, but you can have a very high definition display. You can have a really well done technology in terms of illumination and kind of all of the things that go into it. You can shrink things down, but at the very end of the day, you're still stuck with the resolution of that square. Whatever that square is, you can pack in. However many LEDs you can pack into that. Oh, and by the way, you're still bringing that image all the way around and putting it in front of your face in such a way that it's not really interacting with the real world the way that your eye interacts with the real world. There's a lot of technical kind of background here, but just appreciate that this particular form factor here for micro projection is kind of the way it's done today. That's the way HoloLens works. That's the way the Meta glasses work. And the reason is it's cheap. You can get commercial off-the-shelf products and build these. It's fairly easy to implement. It's relatively low power. In other words, you can do it all on a 4-hour battery on the headset. And there's a long history of it, so it's nothing new. You don't have to really break any molds to do anything different here. However, you're inherently limited on the field of view. You're never going to get past something around 40 to 60 degrees. It's just kind of the basic. You're also inherently limited to the resolution. Now, maybe in 10 years, we'll have some very, very new flexible displays that can do, much higher resolution, some really funky things. But there are just some fundamental computing, or computing is not the right word, but kind of photonics level problems that you have to get around in order to have this type of a system give you the larger field of view. It's also very bulky. So if you look at some of the heads-up display systems now, they're very, very clumsy. And the biggest kind of thing for us is there's no accommodation system. So in other words, you can't vary you cannot vary how far away or not you're focusing, because there's no representation of that within the projection system. So beyond that is something called a virtual retinal display, and this is going to go really fast. But what you see here is an LED, sometimes a laser, which kind of projects to a series of mirrors. And these mirrors, they vibrate at certain frequencies, and basically take that vibration and put that onto your retina. Now you say, well, wait a minute, I don't want to project something on my retina. That sounds very unsafe. In fact, it's a little bit more safe than some of the other systems, to include the microprojection system, because it works with the way basically your brain and your eye works in giving you light as it's supposed to be seen. So I'll run through this again just so you can kind of see. This is really the best video I've found of the way a VRD works. There aren't that many out there. In fact, I think it might be worth us producing one just so we can kind of show people what the difference is. This is from a producer of a headset that's doing something similar to VRDs. So the advantages here are you have basically infinite field of view. Same thing with resolution and accommodation, which are the keys, in our opinion, based on kind of what we were talking about before, to having a successful system. However, it's very expensive. It's very intensive in terms of processing. You have very small systems that you're working with. So these are micro mirrors and MEMS systems that you have to really do no kidding, hardcore engineering for, and it's largely unproven. So we don't have a lot of examples of this used in the real world. So it's kind of, we're making it up as we go on this piece of it. So where we think the specifications are going to be in order for consumers to start adopting head-mounted displays are kind of what you see. So 140 degrees horizontal and 150 degrees vertical for field of view. Something like a 500K resolution display. So you take a 4K display, right? But you need to do much better than that, because your eyes alone do something around the 62 pixel per degree resolution. And 62 pixels per degree basically gives you that 500K. You need a minimum of like 8 different focal lengths in order to give you the range of capabilities that you need to kind of have that kind of true interaction with the world. And you just, by definition, need something greater than 60 FPS because of that. As you move around the world and move your head, really you need to get down to basically 0.2 milliseconds between the time that your system renders an object and when your visual cortex says, okay, I just saw something. That's about the speed that your brain works in terms of visual processing. So that's where we go from there. Not going to get into a whole bunch of detail here on the underpinnings. If you want, from a kind of double ECE perspective, to get into this stuff, it's hardcore silicon photonics. I mean, this is no joke stuff. Doing on-chip photogrammetry, that's kind of part of it. The whole ranging and detection piece, doing it from a micro perspective. So in other words, putting those ultrasonic sensors onto a very slim form factor, very important. And then having some understanding, actually having deep understanding of the micro electromechanical system, or MEMS, in order to kind of build those systems. So that's the display piece of that. The last piece, which I think is almost arguably, I wouldn't say that the most important. I think they're all equally important, but you can have the other two, and that's great. But if you don't have this last piece, then there's not really anything to do. And so one thing that you'll notice when I talk about infrastructure is I don't mean SDKs or APIs. I don't mean the hardware pieces that we've talked about. I mean all of the other things that work with it. So if you think about what is the smartphone infrastructure, in order to have the smartphone do the things a smartphone's supposed to do, right? Which is not only call people, but be able to do email, take a picture, to streaming video, all of the rest. You need at least these three systems: GPS, Wi-Fi, and some form of CDMA or GSM network for the kind of phone function, right? So that's what we consider as the kind of smartphone infrastructure. From a content perspective, I think we all know what smartphone content is. Those are the applications that live within it. And they utilize that infrastructure, hardware and software, all together to give you an experience. Whatever that experience is, whether it's listening to music through the headphone jack as a piece of that infrastructure, or whether it's streaming something utilizing the Wi-Fi and the camera, right? So that's all part of that. The content utilizes the entire infrastructure to make that work, right? So it's important to understand that these are kind of two separate but very connected pieces, that infrastructure piece and the content piece. Well, for AR, we see it as, let me go back one. So AR infrastructure adds a piece of that, and that's that on the right you see, and that's that metaverse that we were talking about, that scanned world. So once you have that scanned world, once you have a very coherent understanding of the world around you, whether it's indoors or outdoors, in addition to just the map of the world so that you can know where you are inside of it, you also have that content piece, which we'll talk about, but you also have all of the virtual elements inside it. So this gives you an example of what a scanned metaverse would look like. So this is a point cloud that was generated after walking through this kind of this market. I think it was in Spain, actually, and this is a point cloud. This is not pictures. This isn't even a mesh. So this is just a series of points, similar to what I showed previously with my living room, with the couch and the little rocking horse chair. But you could today take this and basically glue that onto the real world as you walk through this particular place, and now you've got a real coherent metaverse. And each of the pieces within it, you know, I won't go into the whole thing about recognition and determining what's what and what is where, but once you start being able to identify the different pieces here that are in your world, now you can take the kind of metadata of those and bring them into what we would consider this kind of holistic metaverse approach, where you not only have, again, just what you see here, which is like the scan of the world and an understanding of kind of where you sit within it, but beyond that, this kind of content. So what you see here is just a snapshot, but each of these, you see that they're like achievements, but each of those would be basically the same thing as like on an app store. So you have an application that does, you know, navigation, for example, and that navigation application would use that infrastructure that we just saw, that built world, in order to know where you are and map that new virtual element to it, or any of the options that, you know, we've already shown you some from the HoloLens thing, from the HoloLens video. But it ends up looking the same in terms of application and how you implement that content in that world. And from a content perspective, also, you have to have a 3D representation of whatever you're trying to build. So really the idea that, you know, we're just going to whip out content, that kind of goes away, and we move to more of a 3D centric content generation world, which is orders of magnitude more complicated, but it's also orders of magnitude better in terms of understanding kind of what the context is that we're using it. So that's pretty much all I've got for they kind of stack. I'm not going to run back through it, but I will kind of leave it with that. If you want more information on what we do, just go to pair3d.com, or you can follow us at pair3d on Twitter or Facebook. So with that, I'll jump out of this and stop screen sharing and go back to me. So if anybody has any questions, happy to answer them. I don't know if there's anybody around anymore. Or I can just sit here for another minute. But if that's pretty much it, then I will kind of take that from there. Does anybody else have any questions? Is Jordan still around, or is that the end? I see some people milling around. So anybody, if you're talking, I can't hear you, so you're going to need to unmute your microphone. I see you, but I can't hear you.
Get it.
There you go.
Okay, I will mute the microphone back because it's terrible sound. Just was going to say, Jordan left for a second, and at least people in this room don't have any questions. I don't know about the rest of whoever is watching.
Okay, that's fine. All right, well, I'll just leave it at that then. I'll let Jordan kind of wrap everything up. I do need to go from here, so I appreciate the opportunity to give everybody a talk, and look forward to any other questions. If you do have any questions, just send them to me at andrew@pair3d.com, and I'll take it from there. Thank you.
start the broadcast.